So we are done with data rate. How many bits per second can be transferred on the link? This is given by the Shannon's theorem. Given the link spectrum, Shannon's theorem tells what is the maximum achievable rate. So let's move on to the other two, that is loss rate and delay. In real systems, even when you set the data rate R less than the channel capacity, some errors are inevitable, except that this bit error rate is extremely small if R is less than C. Depending upon the type of modulation, this bit error rate is a function of SNR. For a given modulation, charts of SNR versus B are provided. So here is an example. This chart shows different modulation techniques, basically the way to convert bits into signals. These are the different modulation techniques: PPSK, 16 QAM, 64 QAM, QPSK. For these different modulation techniques, it plots the bit error rate versus the signal to noise ratio expressed in decibels. So what this figure is saying is, if you want a bit error rate of 10 to the power of minus 6, that is something you're okay with. What this figure is saying is, if you want to use 64 QAM as your modulation technique, you need to provide an SNR of at least 18.5 dB. And if you're using 16 QAM, you need to provide about 15 dB. And similarly, if you're using BPSK or QPSK, you need to provide about 10.5 dB. Now this is the bit error rate. Now packet error rate is given by this formula. Even if one bit in a packet is in error, we consider the packet to be in error. So if n were the size of the packet in bits, the packet error rate is given by this. So if you have a bit error rate of 10 to the power of minus 8, this can result in a packet error rate of 0.008%. Now different physical media have different bit error rates. By the way, these are typical values. As I said, it's definitely a function of the modulation scheme that you are using. But roughly, wireless bit error rates are of the order of 10 to the power of minus 6. The twisted pair is 10 to the power of minus 8. Fiber optics is very good. It's of the order of 10 to the power of minus 9 to 10 to the power of minus 12. So the final question, what is the time required for a bit to propagate from the beginning of a link to the end of the link? So this depends on the speed of light in the medium and the distance. It's basically given by d over s. One point I wish to emphasize is that the transmission delay is very different from the propagation delay. Transmission delay is related to how much time it takes to send the packet. So this is given by length of the packet over the data rate. Let me make this clear through an example. Suppose the transmitter and receiver are connected by a link that spans 2000 kilometers. So we have D as given by 2000 kilometers, that is 2 into 10 to the power of 6 meters. And let's assume that the speed of light in this particular media is 2 into 10 to the power of 8 meters per second. Let's also assume that this link supports a data rate corresponding to 1 megabits per second. In other words, the rate at which you are pumping bits into this media is 10 to the power of 6 bits per second. And let's assume that the packet size is 1000 bits. Starting at time t is equal to 0, the transmitter starts to put the bits into the media. So it's going to take some time to finish the transmission of the packet. So this is called the transmission time. Now this transmission time, as given by the formula, is equal to P by R, that is equal to 1000 over 10 to the power of 6. This is nothing but 1 millisecond. So this is the transmission time. The first bit that the transmitter put on the media is going to take some time to reach the receiver. So this one will reach the receiver only after some time. Now this time for the first bit to come from the transmitter to the receiver is the propagation time. Now the propagation time is given by d over s, that is equal to 2 into 10 to the power of 6 by 2 into 10 to the power of 8. This turns out to be 10 milliseconds. This is the first bit comes here. Following the first bit, all the other bits are also going to come. So by the time the complete packet, so this is the time at which the complete packet reaches the receiver. So this is 10 milliseconds, this time, and this is 1 millisecond. So for the receiver to fully receive the packet, it takes 10 milliseconds plus 1 millisecond, that's equal to 11 milliseconds. So why did we cover all this theory? It basically sets the background for understanding the goals of modulation. One of the goals of modulation, that is converting data into signals, is maximizing bandwidth efficiency. This is given by data rate over bandwidth required. Now the data is typically sent at a certain rate that is given by the data rate, and when you convert this data into signals, the signals require certain bandwidth for recovery without errors. So that is the bandwidth required. Naturally, when you want to support high data rates, you typically need more bandwidth, but the idea here is for a given bandwidth to extract the maximum data rate out of it as possible. Basically, try to reach Shannon limit. Now in real systems, the bandwidth efficiency varies. There are systems with very low bandwidth efficiency and systems with very high bandwidth efficiency. These are some of the advanced systems that are being developed these days. Another goal of modulation is power efficiency, which basically captures the energy required per bit. Basically, higher energy per bit leads to better signal to noise ratio. Again, the goal here is to minimize the signal to noise ratio required for a given bit error rate. Basically, this conserves energy. And there is always a trade-off between bandwidth efficiency and power efficiency. In other words, you cannot achieve high bandwidth without sacrificing more energy. Higher bandwidths typically mean smaller bit intervals. And unless you increase the energy in this bit interval, you cannot maintain the same bit error rate. Let me show this through an example. This figure is from before, basically a plot of the bit error rate versus SNR for the different modulation techniques. In Wi-Fi, 16 QAM gives a bandwidth of about 32 Mbps and 64 QAM gives a bandwidth of about 54 Mbps. And for a given bit error rate, the SNR that is required for 16 QAM is about 15, whereas this is about 18.5 dB. So as you can see, you can provide this increase in data rate from 30 to 54 Mbps, provided you provide a 3.5 dB increase in the signal to noise ratio. What this boils down to is, unless you put more energy into the bit, you cannot achieve this increase in the data rate. So a quick summary of what we learned in this video. So through Fourier analysis, we saw that signals have a frequency domain representation. We saw the bandwidth occupied by these signals. And then we looked at some theory. Basically, Shannon showed what is the maximum capacity that you can achieve on a link. In reality, this is often dictated by the medium as well as the type of modulation you are employing, basically how you are converting data into signals. Now we saw earlier that links distort the signals, and thereby in recovery there could be errors, and the kind of errors you are going to see is again a function of how strong your signal is relative to noise as well as the type of modulation you are employing. These are provided in the form of charts. And we also saw that the speed of light in a media varies depending upon the media, and this accordingly dictates the delay it takes for a bit to propagate in a media. Based on all this, we also understood the goals of modulation, basically bandwidth efficiency and power efficiency. Now we are ready to look at modulation.